from Montreal. And so please, Richard.
Okay, thanks. Thanks a lot for being there, all of you. I have not given a talk for about a year and a half or 2 years. I feel like going back to school, in fact. So I want to thank Javad and Ryan for their invitation. I'm very happy to give this talk. Okay, let's go. So I will talk about some old, not so old, but little bit old interpolation formula I worked on for many, many years with many collaborators. Dimitar Drianov, who's in Montreal now, Stefan Rouchavay, who is in Evans, and Luis Salinas also. We worked on this thing for a dozen years about various things we did with that. So the interpolation formula is what you see there beside the end. You take a polynomial p of degree at most n with complex coefficients, if you wish, and then these differences there, p of e to the I theta minus p of e to the minus I theta over twice sine theta times I. This can be written as essentially a sum involving the values of the polynomial at the points I, j, pi over n and minus I, j, pi over n. And we know explicitly what these coefficients are, Cn, cos of j pi minus cos of n theta over n, cos of j pi over n minus cos theta. And these things there, this won't be important for the talk, but in the summation formula, the two little bars there, it means that when j is 0 or j is n, you divide the whole thing by 2. Instead of Cn, you take Cn over 2, but this is not important. So these coefficients have a nice property. The sum of the absolute value with my definition there will be at most n, where n is the degree for any real theta. Okay, so I don't know how we came through this this formula, to tell you the truth. Once a student asked me, and I said, oh, I dreamed of it first, and then my tricky friends helped me to find a proof. But it turns out that the formula has quite amazing consequences. A few of them are listed there. First of all, we gave several proofs of this formula with Drianov and with Stefan, and then with Salinas. They look different, these proofs, but they're essentially based on a Lagrange interpolation formula, a little bit tricky, or formulas to integrate functions in a numerical way, you know? So this is what we've been using all the time. So for example, you can obtain from this formula refinement of the inequality of Bernstein for polynomials on the unit disk. This is the first formula which is given there. That gives you that p prime of a point on the boundary of the unit disk is never more than n, okay, times weird expression here, maximum of values, of certain values. Notice that the theta appears also here, correct? But this is of course, never more than the maximum of the polynomial over the unit disk, okay? So this is quite an interesting refinement. This is a discrete refinement of the inequality of Bernstein, Okay, then we used it, and we got more excited at this point to get a proof that was new of the inequality of Markov for polynomials, this time on the interval -1, 1. Everybody knows this is the refinement of the inequality of Markov due to Duffin and Scheffer, where the maximum of the polynomial over the interval -1, 1 is replaced by the maximum of the polynomial at n+1 values, correct? And the factor here, of course, n squared is the correct one. We were very happy when we have done this. I'm not going to discuss the proof we got also, but it was usually in approximation theory, the inequality of Markov or Duffin-Schaffer and the inequality of Bernstein for polynomials on the unit circle, they're seen as, okay, relatives, but far away relatives, okay? And one interesting point of our work was that we had an explanation for the n squared here. In fact, the n squared comes from the fact that two iterations of the Bernstein inequality, the way we got it here, two iterations of it, it gives you the Duffin-Schaffer inequality. So we were really happy about this. Another point is that the formula contains the famous interpolation formula of Marcel Ries through the following trick. If you take a polynomial, a trigonometric polynomial, Tn, with real and or complex coefficients again, and if you consider a polynomial defined by e to the n theta, e to the in theta times t of theta, this will be a polynomial of degree 2n. If you apply our interpolation formula with, of course, n replaced by 2n, what you get after a little bit of algebra work is the Marcel Ries interpolation formula. And therefore, our formula implies also the inequality of Bernstein for trigonometric polynomials. It is well known that the inequality for trigonometric polynomials follows from the Marcel Ries interpolation formula. And finally, go back, Javad, please. Okay, this thing below here, I will discuss a little bit later. We obtain an upper bound for these special divided differences, correct? In terms of the values of the polynomial at the points, the 2n roots of unity, right? Nice, okay. Let's go. So one day I was reading old papers and I saw this inequality there that really surprised me. People.
Richard, I think Oli has a question.
Oli Roth.
Oh,
Yes.
no, sorry.
No, it's, go ahead. It's my mistake.
Okay. I'm sure he could not resist. I invited him to go for a beer, you know, and maybe that was his reply coming, but that's all right. So I found this inequality here in a book, and actually I was in Germany. This divided difference here, the maximum of it over the interval from 0 to 2 pi is at most n times p to the I theta minus p to the minus I theta over 2, and you take the maximum over 0 to pi. Okay, after the inequality I showed you before, I was really surprised by this one. I did not it gave me doubts that maybe our work was complete. There was a flaw somewhere because I could not see how the two inequalities could hold. And then I digged into it, and then I found a paper of Paul Nevai from 2014, where he shows that the inequality of Schur is actually equivalent to these three facts here. An inequality more or less Bernstein type for odd trigonometric polynomials, or this inequality here, which those who are interested by approximation theory, or at least elementary parts of it, this is involved in the proof of the classical Markov inequality for the case for the first derivative, eh? Or else it's equivalent with the Bernstein inequality for trigonometric polynomials. Now, as I said before, we can obtain the Riesz interpolation formula from our formula, and therefore from our formula follows this inequality here, and therefore the inequality of Riesz-Schur follows from our formula also. Okay, you can go ahead. Now, you see, that was my problem. We have these two inequalities which apparently hold together, right? The first one gives an upper bound for the divided difference, an upper bound which is of discrete type, okay, involving the 2n roots of unity, correct? And then the other one of Riesz-Schur gives this thing. What really bothered me was the minus there and the plus there. To me, it made no sense. But I'm very naive also, maybe ignorant a little bit. So I had no idea. And then, of course, we raised the question, which is one inequality better than the other one? This is what I thought in the beginning, that these respectable people had done serious work and gotten an inequality that would have been implied by our inequality, or the other way around, rather. And what I will show you in this talk is that no inequality is universally better than the other one. They cannot be compared. Okay, so first thing, the trivial affair is that this is the left member of the first equation on top. This here is sometimes less than the right-hand member for certain polynomials. This is easy. You take a polynomial of the type a plus b z to the n, for example. The inequality there says that n b times the maximum of sine n theta will be less than this quantity to the right. This amounts, after a little bit of thinking, to the fact that the absolute value, the norm of b, will be less than the maximum of the norm of a plus b and a minus b. And this it will be for sure true if the norm of b is less than absolute value of a plus absolute value of b. In other words, if the length of the complex number b is less than half the length of the complex number a, the inequality on top will hold for the polynomial a plus b z to the n. Okay, so sometimes one inequality will be better than the other one, at least sometimes. Here is a case. I'm sure there are many other cases where this is true. Okay, let's go. Now, the nice thing is that we were able to find out that the inequality in the other direction also holds sometimes. And here, we were not able to find a completely trivial thing. So this is what I will talk about a little bit now. So on top is what we want to prove. So the ends go away. Okay, and now what you do is the following. You look at the unit disk and you take a conformal map from the unit disk to this ugly rectangle there. Important point will be that 5 alpha will be much bigger than alpha. This is what I want. I want to be the rectangle to be elongated. And then we look at these polynomials here. Those who are familiar with the work of Rouchavaille, for example, must know that he has used the properties of these polynomials a lot, and maybe the idea came from him. I don't remember. So you look at these polynomials here. They're variants of Fourier polynomials, if you wish, okay, in the algebraic disguise, say. And it is well known that these polynomials have a real part greater than 1/2. And because the value at the origin is 1, this implies that the polynomials have a representation like this here, where mu n there is a probability measure. Okay, this comes from the Qn of 0 equal to 1. And the existence of this measure, this is the so-called Erglotz formula, if you like. Correct? Let's go. All right. So now you take the Hadamard product convolution of these Fourier polynomials with the conformal map. Correct? So what will that be? Oh, here is a mistake. This will be convolution of f with Qn, which is this thing. And at the end, you will get this. Some sort of Stieltjes integral of f of zeta z, integral taken along again against a probability measure on the boundary. Okay, now this rectangle R, I choose to be symmetrical with respect to the real axis. So this function f will have a real Taylor coefficients, and therefore my polynomial Pn I defined here as also real coefficients, real Taylor coefficients of the polynomial. Okay. Also, another thing is that this formula on top there, this is like convex combinations of the values of the function f, because mu n is a probability measure. Look at it this way. So it means that the image Pn of D has got to be included in the convex domain R, of course. Okay. And now we get some explicit expression for the convolution of f with q. So you're going to get this partial sum of nth partial sum of the function f minus z derivative of the nth partial sum divided by n plus 1. This is obvious properties of Hadamard product. Good, good, good. So what does it mean? First of all, these polynomials Pn, when n tends to infinity, they of course tend to f. Let's be careful, not uniformly on D, but uniformly on compact subsets of D. This is rather clear because this thing here, Z sigma n f sigma n prime fz, this tends to zf prime, correct? But the n plus 1 there make it go to 0. Okay, so these polynomials, they tend to f. Very nice.
Yeah.
On D.
Yeah. Richard, what was mu here?
A probability measure, because these polynomials Qn, they have the real part greater than 1/2. Okay, so you can represent them as, this is the formula of Erglotz, if you want to use down-to-earth language.
Yeah, thank you. Thank you.
Nice. Okay, let's go. Okay, so what we get at the end is what? we look at the maximum for j between 0 and n of Pn of the roots of unity there, right? Over 2. So because the coefficient Pn, a polynomial Pn has real coefficients, this is the conjugate there. So what is that? This is the maximum of the real part. And this, the thinness, you see how large the rectangle was. This can be only at most alpha. Eh? For the real part, we have almost between minus alpha and alpha. So, right. And now, what do? You choose R large enough and N large enough, and then you go like this. 4 alpha will be bigger than the maximum of the imaginary part on mod Z equal to R, if you prefer. Why is that? Because the damn thing will fill the rectangle, which has height close to 5 alpha, right? Okay. So what will happen? The maximum here for mod Z less or equal to R will be, of course, less than the maximum for mod Z less or equal to 1. It is the maximum for mod Z equal to 1, this is maximum principle. And then this is exactly this quantity here. And this turns out to be Pn of e to the I theta minus Pn of e to the minus I theta over 2. We look at maxima, this will be conserved also. So we have this inequality. And this is what we wanted to have. Correct? So this is amazing. These two inequalities, they cannot really be compared. Okay, now what we wanted to do at the time, and we never succeeded to do, you see this inequality of Dauphin and Scheffer, and the case n equal to 1 for the case for the first derivative, it's not so hard to handle, okay? It's the original proof of Markov was terrible, but then Dauphin and Schaffer, when they proved their refinement, they simplified it a little bit, but nevertheless, it's still involved in the case of Dauphin and Schaffer, functions of exponential type and properties of these functions. We had always the feeling that something simpler should be possible. And you see, that's it. We got, this is just an isomorphism for between Pn and itself. You pass from the polynomial big P to a polynomial small p this way. And then you compute P prime of cos of phi. That gives you, now you use our formula, okay? That gives you something like this. And the sum of these numbers, Cn J0 and Cn T phi, each sum is at most n, okay? So this is why you get the n squared, correct? And then for derivative of order bigger than 1, you have a similar formula, but okay, it looks simple, but it is rather disgusting. Actually, because of this decay there, this is iteration of some derivatives, each time divided by the sign. If there is justice on Earth, it should be possible to get the bound we need to get the inequality for the Kh derivative. But as I said, we never were able to do this. You see, I don't know if you remember, but the bound for the quotient of P prime over P, the maximum of P prime over an interval over the maximum of P, this bound in the case of the interval from -1 to 1 is not so nice, eh? You have these n squared and then n squared minus 1 squared, blah, 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 and then products of odd numbers below. I don't know how we can get this. We have to rearrange, I think, these sums and try to get it. but we were never able. And then I'm raising the question, is it possible to do so? I have no idea. Maybe somebody told Stefan and Evans that how it can be done, but I have no idea. Okay, thank you. Thanks a lot.
Thank you, Richard, for this talk.
Yeah.
And if some person has any question, you can speak in the chat or ask your question directly.
Or even better, send me a mail. I will send you the paper. This the paper has been published a year ago or something like this. But really, that would be cute to do this.
Richard,
Yes.
a very naive question. Sorry for this elementary question, but you have in the combination you have, it's always conjugate. You have z and z bar. Like
Yeah. Of course.
e to the I theta, e to the minus.
Yeah. Of course.
Why not reflection with respect to the other axis, for example? Is it working?
That could be interesting. I don't know if you would get a nice formula, but I'm sure there exists a similar formula if you reflect on the other side. Why not?
Mm-hmm.
This would be okay. You see, you have to be careful because to get, if the goal is to get exactly what Dauphin and Scheffer got, you want to have the maximum of the polynomial at the point cosine of j pi over n. Now, if you do a reflection across the y-axis, you're going to get maximum at some other points somewhere. Maybe points on the imaginary axis or God knows what. Correct? But that would be a different thing. I'm sure this is feasible. But you see, before asking me this question, you're a man with ambition. For me, what makes sense is to try to recover a classical result with this crazy, this formula. I really don't know how to do that.
Thank you.
You're welcome.
Any other question? So if not, let's thank the speaker again.
Thanks a lot. Thanks a lot.